Random forest is the 8th topic in our machine learning series, and this is the first lecture on it. Random forest is an ensemble model that uses multiple decision trees. It is one of the most widely used machine learning algorithms because of its strong performance and stability. In this lecture, we'll build the foundation for understanding random forest. First, we'll briefly talk about the history of random forest, and then look at a high-level overview of how it works. Then we'll move on to Bootstrap Aggregation, or bagging, which is the ensemble method behind random forest. Next, we'll talk about data subsampling, including both row-wise subsampling and column-wise subsampling. And finally, we'll finish with variance reduction through subsampling, where we'll use the math to see why subsampling leads to more stable predictions. According to Wikipedia, in 1995, Tin Cam Ho proposed the random subspace method, which randomly selects features during training. Later, in 2001, Leo Breiman combined Bootstrap Aggregation with random feature selection and formalized the random forest framework that we use today. Random forest is widely known for its strong predictive performance and relatively low risk of overfitting. Throughout this series, I'll refer to the following 3 resources, but I'll mainly rely on references 2 and 3. The first resource is the original 2001 paper by Leo Breiman that introduced random forests. The second resource is the Random Forest webpage by Leo Breiman and Adele Cutler, which explains many advanced features and applications of random forests in detail. Among those features, we'll focus on out-of-bag scores, the proximity matrix, missing value imputation, and outlier detection in the later lectures. The third resource is the YouTube channel StatQuest, which provides a very clear explanation of the proximity matrix. Now, let's take a look at the overall structure of random forest. Random forest is a bagging-based ensemble method that uses multiple decision trees. Let's first look at the diagram below. From the training dataset, we repeatedly generate multiple sub-datasets through sampling. If the original training dataset contains n samples, then each sub-dataset is usually generated with the same number of samples, which is also n. The sampling process uses random sampling with replacement. In other words, the same sample may be selected multiple times. In practice, the sub-dataset size could be smaller than n, but in standard bagging, the Bootstrap sample size is usually the same as the size of the original training dataset. Next, we train a separate model on each sub-dataset. General bagging can use many different models, such as support vector machines or logistic regression. However, random forest specifically uses decision trees. If we generate t subdatasets, then we will also train t different trees. That completes the training process. Once training is complete, we pass the test sample through all trained trees, and each tree produces its own prediction. Then we combine all of those predictions together. For regression problems, we take the average of the outputs. For classification problems, we use majority voting. This is the general bagging framework used in random forest. Bagging has a parallel architecture like this. Random forest extends this idea further by performing not only row sampling, but also feature sampling. Feature sampling means randomly selecting a subset of features during training. Row and feature sampling help reduce the correlation between trees. Each tree is typically grown to its maximum depth without pruning. Deep unpruned decision trees may strongly overfit the training data. However, random forest reduces overfitting by averaging many decorrelated trees. Therefore, pruning is usually unnecessary for the individual trees inside a random forest. Now let's take a brief look at how random forest makes predictions. When a test sample is passed through all trained trees, each tree produces its own prediction. In classification, suppose the outputs are 2, 1, 2, 2. In this case, the final predicted class would be class 2, because class 2 receives the majority of the votes. In regression, the final prediction is obtained by averaging the outputs of all trees. Now let's look at how random forest performs data sampling. Random forest performs both row-wise sampling and column-wise sampling. Let's say we have a dataset D. Along the rows, we have data instances. Along the columns, we have features. Let the number of data instances be n, and let the number of features be p. First, we perform row sampling to generate the first subdataset. Sampling is performed with replacement. For example, suppose the sample data instances look like this. A total of n samples are selected. Because sampling is performed with replacement, the same data instance may appear multiple times. Next, we use this subdataset to build a decision tree. Before splitting a node, we randomly sample a subset of features from the full set of p features without replacement. This is the feature sampling process. The number of selected features is determined using the following formula. These are empirically validated default values commonly used in random forest. For classification problems, the square root of p is commonly used. In some cases, smaller values, such as log base 2 of p plus 1, may also be used, especially when the number of features is very large. For regression problems, p divided by 3 has traditionally been used as a common heuristic. In this lecture, we will use the square root of p for classification problems. Of course, this value can be adjusted depending on the dataset. Here, p represents the total number of features. If p equals 9, then m becomes the square root of 9, which is 3. Next, we evaluate the sampled features using a criterion such as information gain or Gini impurity. Then we select the best feature and the best split point. Let's say x1 is selected as the best feature in this example. Then the actual split would look like this. Here, x1 is the best feature, and A is the best split point. Using this rule, the root node is split into left and right child nodes. Then, whenever another child node is split, we again perform feature sampling. We again randomly select M features from the full set of P features. Suppose X7, X3, and X4 are selected this time. Then we again choose the best feature among them. For example, X4 becomes the best feature. In this way, feature sampling is performed every time a node is split. At each node, a random subset of features is selected from the full feature set. Feature sampling is independently repeated at every node. Because of this independent sampling process, the same feature can be selected multiple times within a single tree. In this example tree, X7 was selected again. By repeating this process, we continue growing the tree deeply. Next, we perform row sampling again to generate another subdata set. This time, a different set of data instances will be sampled. Then we use this new dataset to build another decision tree. Again, feature sampling is performed in the same way as before. By repeating this process, we can build many different trees. The purpose of subsampling is to reduce the correlation between trees. As a result, the variance of the final prediction becomes smaller. If we do not perform row sampling, then every tree would be trained on the same dataset. As a result, the trees would become highly similar, greatly reducing the effectiveness of the ensemble. Feature sampling further reduces the correlation between trees. Without feature sampling, many trees would repeatedly select the same important features. For example, if X1 is the most important feature, many trees may choose X1 for the first split. Even if row sampling changes the subdata sets for different trees, X1 may still be the most frequently chosen feature in the early splits. As a result, many trees may still develop very similar structures, again reducing the effectiveness of the ensemble. Next, let's look at the math behind why data sampling reduces prediction variance. For regression problems, the final prediction is obtained by averaging the outputs of all trees. Here, X represents a test sample. The prediction of the ith tree is denoted by Ti of X. Now let's apply the variance operator to both sides of the equation. On the right-hand side, the constant term 1 over t can be factored out of the variance as its square. Since the variance of a sum can be expressed as the sum of all pairwise covariances, we can rewrite the right-hand side as follows. When I and j are the same, the covariance becomes the variance. When I and j are different, the terms remain as covariances. For simplicity, we assume that all trees have the same variance, denoted by sigma squared. Next, using the definition of the correlation coefficient, we can express the covariance terms using the correlation coefficient rho. Then we can simplify the variance expression to the following final form. Here, rho represents the average correlation coefficient between trees. Since row-wise and feature-wise sampling make each tree use different training samples and different features, the correlation coefficient rho becomes lower. As we can see from the final equation, when rho decreases, the variance of the final prediction also becomes smaller. In addition, increasing the number of trees generally leads to more stable predictions and lower variance. But notice that the variance does not go all the way to zero because the trees are still correlated with one another. As we can see from the equation, the first term remains even as the number of trees approaches infinity. Using fewer features during feature sampling often reduces the correlation between trees, which helps reduce variance. However, if too few features are used, the individual trees may become weaker, which can increase bias. This trade-off is one of the key design considerations in random forest. This explanation was based on the following reference. So far, we've looked at the basic ideas behind random forests. In the next lecture, we'll implement random forest from scratch and compare it with scikit-learn's implementation.